Hi folks, Chris McClure here. We had a couple of day hiatus, but we're going to get back on track here and go full bore finishing up chapter 6 here. Now, the last few lectures we were talking about the normal distribution in section 6.2 and 6.3. Now we're going to talk about sampling distributions in section 6.4. What in the world is a sampling distribution? Well, what we mean is a sampling distribution of a statistic. And generally speaking, what a sampling distribution of a statistic is if you were to repeat an experiment many times, each time that you do a statistic, each time that you do a trial of an experiment, you calculate a statistic, like the mean or the standard deviation. Let's just focus on one, the mean. So each time that you repeat the experiment, you calculate the mean. Now, suppose that we have done 10,000 trials of the experiment. Each time that we calculated a mean. Now we have a list of 10,000 numbers, means. What is the distribution of that set of means? Well, we shall see. We can ask the same question of any statistic. That's what we mean by sampling distribution of a statistic. One of the caveats is that the sample has to be the same size each time that we do the statistic. We're going to be talking about the sampling distribution of the mean, or sample proportion. Also, you'll see it for the variance, which also applies to the standard deviation. Okay. Now, the sampling distribution of the mean, of the sample mean, is the distribution of all possible sample means, with all samples having the same sample size n taken from the same population. Now, the sample means target, the target of the sample means, is going to be the value of the population mean. So what that really means is that if we were to take all possible samples of the same size and then took the mean of that set of sample means, we would really expect to get exactly the population mean. Another way of saying that is that the expected value of the sample mean is going to be the same as the population mean. By the way, the distribution of the sample means tends to be a normal distribution. And this is a very important role as we go forward through the rest of this course. Sampling distribution of the variance tends to be what we call a chi-square distribution, which we will encounter in a future chapter. But it's not going to be the normal distribution. It's going to be a skewed right distribution. But the target of the sampling distribution for the variance is going to be the population variance, as in the expected value of the sample variance for any one trial is going to be the population variance. And then the proportion, sampling distribution of the proportion, is the distribution of all possible sample proportions, meaning, you go and take sample the same size infinitely many times, or however many times that you possibly can, all possible samples of the same size. Each time you calculate a proportion, okay, and we'll be looking at that distribution, you'll see that it's going to be somewhat normal-like. By the way, the letter P here means population proportion. P hat means the sample proportion. What we mean by sample proportion, for example, is what fraction of people in your sample said yes, that they support Smith for governor, for example. Sample proportions target the value of the sample proportion. And the distribution of the sample proportion tends to be normal. What an unbiased estimator is, and I'm gonna pause right there, and in parentheses say an estimator is what a statistic is. Sample mean, for example, is an estimator for the population mean. And the sample standard deviation is an estimator for the population standard deviation, etc. Sample means, sample variances, sample proportions are said to be unbiased estimator. What does it mean for an estimator to be unbiased? It means that they target the population parameter, and that the expected value of a sample mean is going to be the population mean, and the expected value of a sample variance is the population variance, etc. And so we are going to use those statistics to calculate the true population parameters. Biased estimators, for example, median, range, and, by the way, standard deviations, are all examples of biased estimators. They do not target the population parameter. Even though standard deviation is not an unbiased estimator, even though it's biased, we still use the standard deviation to estimate the population standard deviation, because the bias is relatively small. So we're going to take a look at an example here. We're going to repeat in this process. We're going to roll a single fair die 5 times. So think about sample size 5. And we're going to count the number of odd numbers that result. So we could either have 0 odd numbers, or 1, or 2, or 3, or 4, or 5 odd numbers that come up with 5 rolls of the die. So x, by the way, x, random variable x, is going to be the number of odd numbers that come up. So odd numbers, as in a 1, or a 3, or a 5. So we're going to count the number of times that either a 1, or a 3, or a 5 comes up. Now, just as an aside, half of the numbers that are on the die are odd. So excuse me, it's 1/2, I should say. 1/2 the numbers are odd. So there should be a probability of 1/2, because each side is equally likely. There should be a 1/2 probability of getting an odd number. Alright, so we're going to figure out the sampling mean for the sample mean. Excuse me, we're going to talk about the sampling distribution, I should say, for the means, for the variance, and the proportions. What do we know about the behavior of all sample means that are generated as this process continues indefinitely? Well, we will see. Thank goodness for the ability for computers to do simulations. So we had submitted in an experiment this scenario of having the computer roll a single fair die 5 times and do that 10,000 times. For each 5-roll trial, the computer is going to count the number of odd numbers that come up. So now I have to backtrack. For this one, actually X is not the number of odd numbers. X is just going to be the number that comes up for each trial. So X could be 1, 2, 3, 4, 5, or 6. The number of odd numbers, that comes in later when we talk about proportions. But for this one here, X is just simply the number that comes up for each roll of the die. So X bar means the average of the 5 numbers that come up. Now, if you were to simply take 1 plus 2 plus 3 plus 4 plus 5 plus 6 and divide by 6, you would get 3.5. So we would expect that the population mean is 3.5. Meaning, if we were going to do this an infinite number of times, in rolling the die 5 times and taking the average of the 5 numbers that come up, we would expect the average of those infinitude of trials to be 3.5. But here's the list of numbers that the computer's generated after it's done 10,000 trials. 3.4, 4.4, 2.8, ... And then for those 10,000 numbers, we have the computer generate the histogram. Thank goodness for technology. And notice that, by the way, that this is somewhat normal. And with the peak right above 3.5. Okay? If we were to compute the variance, again, where X is going to be the number that comes up in each of the 5 rolls of the die, if we were to compute the variance of those 5 numbers for 10,000 trials, here are the variances. 1.8 is the variance for the first trial. 2.3 is the variance for the second trial. 2.2 is the variance for the third trial. ... 10,000 times we have 10,000 variances. And if we were to look at the histogram for this list of variances, notice that we have a right skewed distribution. Again, I'm going to just whisper in your ear the distribution called chi-square. Now, the mean of those 10,000 variances would work out to be 2.88. I won't bore you with the details, but it'll turn out that the population variance is 2.9. Again, in a later lecture, you'll see exactly where that comes from. So this 2.88 as the average of these sample means is very close to the theoretical population variance of 2.9. And again, notice the distribution of those variances is skewed right. Think chi-square. Chi-square is a very special distribution that we will come into contact with later on. Now here we get back to the proportions, and proportion is going to be the number of odd numbers that come up divided by 5. So X is going to count the number of odd numbers that come up. X could be 0 or 1 or 2 or 3 or 4 or 5. So that means that the proportion could be either 0, 0.2, 0.4, 0.6, 0.8, or 1. So we're going to do our first trial, roll the die 5 times, count the number of odds, and then compute the proportion of odds for the first trial, 0.2, so that's 1/5, 1 out of 5. Numbers come up odd. Second trial, you had 0.4, 40%, 2/5, as in 2 out of 5 numbers being odd. Third proportion is 0.8, ... We have 10,000 proportions. Here's a histogram of the proportions over here to the right. Notice that it's somewhat normal looking with the mean of 0.5. Of course, if we have an infinite number of trials, the histogram would look just like a normal distribution with the mean of 0.5. So when we do simulation or thought experiments for statistics and probability, we often care about whether we are sampling with or without replacement. So why do we care so much about sampling with replacement? Well, let's look at sampling without replacement, where you have a bag of gumballs, for example, and you reach into the bag, you look at the color of the gumball, and then you eat it. Well, once you consume that gumball and you don't put it back, then that changes the probabilities for the next draw, which is not necessarily a bad thing. And in fact, sampling without replacement would have the very practical advantage of avoiding wasteful duplication whenever the same item is selected more than once. However, we have to deal with changing probabilities, conditional probabilities, from one draw to the next to the next. We are interested in sampling with replacement for the following reasons. Number one, when selecting a relatively small sample from a large population, it makes no significant difference whether we sample with or without replacement. Look, if you got a bag of 10,000 gumballs, just taking one gumball out is not going to really change the probabilities from one draw to the next. You can take one gumball, note the color, eat it, and then keep moving, as long as your overall sample size is very small relative to the total number of pieces. Sampling with replacement results in independent events, which is very important when we calculate probabilities. Independent events that are unaffected by previous outcomes. And independent events are easier to analyze and result in simpler calculations and formulas. So when we talk about computing binomial probabilities, for example, we assume that each individual Bernoulli trial is independent of each other. If they weren't, then the calculation is no longer for a binomial probability, it's something different. Okay? Called hypergeometric, which we won't really necessarily talk about in this class. And here's a caution here, is that we have to make sure that our experiment / statistical study involves samples that are simple random samples, and that each sample is equally likely as any other sample for the same size. But just understand, though, that some samples are better than others. If you had designed an experimental regime in which you're doing sampling using, say, convenient sampling, or you are plagued with voluntary response problems because you didn't design your sampling correct, then you're going to have very bad results because your sample is not going to be representative of the population. In order for your result to have any chance of being good, you need good data. You need to have a sample that has a very good chance of being representative of the population. Okay? And that chance is not good at all if you're only doing voluntary response. So think about those internet polls. And same thing with convenient sampling, where you go into your apartment building and knock on the doors of the people who reside there, and then you purport that sample to be a sample of the residents in your town. Not good at all. So make sure that you are getting a good simple random sample. Okay, so with that, that's it for this section. I'm going to record another section here in a couple minutes. The next one, section 6.5. Okay, so take care, and I'll see you next time.